Hello everybody and welcome to the 14th Machine Learning with Python and Scikit Learn with Investing tutorial video. In this video we're going to be basically building on the last video, and we're going to add some features, add a lot more features here, as well as talk about another issue. So a pretty important issue is the following. Let's just bring up an example. With say Apple computers, obviously I've already kind of brought up the issue of say what kind of sector are they in? Is this technology? Is this a bank? Is this a mining company? Is this a consumer? Do they make shirts? So this is, like Aeropostale or something like that. Are they a restaurant like Chipotle? Something like that. You want to classify these things into sectors. But another issue is just kind of general normalization. So typically in machine learning, people say, hey, we think that you want to have all of your data points be between -1 and +1. Now it's okay if you need a little bit more granularity there, so to speak, or at least magnitude, and you can do -5 to 5. That's okay. That's acceptable. But what's challenging is if some of your data goes from -1 to 1, some of your data goes from -15 to 9,000, and some of your data goes from -1 billion to 72 billion. It's okay. You can still kind of run that through your machine learning algorithm, but it's not best practice, so to speak. So for that reason, we want to use some sort of scaling of our data and kind of get everything as close to normalized, i.e. as close to basically kind of the same range as everyone else. So the first thing that we're going to go ahead and do is talk about that. Now, there's a lot of ways you can normalize your data. One way I can think of would be, say, with our pandas data frame, for each column, we could say, each column you could find the minimum and the maximum. And you could say the maximum is 1, the minimum is -1, boom, done. That's a problem because you obviously are, from time to time, you're going to have massive outliers. So then you could say, okay, the average is 0. And then we'll convert, the real average to 0, or let's say, 0.0001. And then everything else will convert using the same formula. Well, that's okay, but you're still going to have this scaling issue where some things are going to have a different maximum than others, especially when you consider variance. So then you're like, okay, we're going to use standard deviation. We're going to take standard deviation and we'll apply this to our formula, and we'll take standard deviation, and that'll use the deviation from the average to the max, and we're going to do that. But that's going to have a lot of problems too. So as usual, I'm just going to say that someone's already done it for you, okay? And with Scikit Learn, it's no different. We're going to use a simple function here. So we're going to use this function on x, which is what needs to be normalized. And we're just going to say, now we're going to redefine x as x equals preprocessing.scale, and we're going to scale x. Okay? And now we need to actually import preprocessing. So from sklearn import svm, and then also we're going to import preprocessing. So preprocessing is a Scikit Learn kind of module of its own that helps you pre-process your data before you use it for training. It's really helpful. We might touch on some other things, but for now we're just mostly interested in this scaling function. So we will scale our data with that, and we could really just take it from here. So we're still going to 100. So for example, we can run this really quick. I think this pops up pretty fast. So you can already see that it looks almost identical, but it's been scaled. I can't remember how off this stuff was, but okay. So for here we've got a 5, and here is a 10. So let me close this, and we'll take away the scaling. Just curious if this makes a huge difference in this graph. Right. So you can see that now from before we were in almost single digits here, relative integers, but here we're going all the way up to 600. This one goes up to all the way 100. And looking at our output, it looks almost identical. It really does. So when you only have like 2 features or something, that's okay. But again, as always with machine learning, where it really shines is with a lot of features. So we'll go ahead and leave this there. And now what we want to do is use a bunch of features. So as usual, I'm going to go ahead and just say I see no point in you guys making this list yourself. So I'm going to just copy and paste the list. and you guys can, I'll put it in the description, as well as usually I post the sample code from all my videos on pythonprogramming.net, so you can also check there, but it will be in the description of the video what you absolutely need. So I'm going to copy and I'm going to do paste. And this is a huge list of features. If you'll see, I've kind of made it its own constant. In theory, we could call features actually more better features like that. Doing my best to be Pep 8, but it's really hard to be Pep 8 when you're making a video, so sorry guys. Anyway, features, caps, and then this is all the features that we're going to consider. I believe it's 35 features. We'll come down here and we'll just say, actually we don't need to put anything there. We can just make that an empty, and all we need to do actually is capitalize this features, so features like that. And that should be it. So now we will take all this data, we're going to pass it through X and Y, and then we're going to basically run it. Now, we'll leave this colon 100 there for now. I don't really think it's necessary, actually. I think this should all process pretty darn fast. So I'm just going to comment out that line. We'll return to it if we need it, but we should be able to do that pretty quick. We're not going to be able to graph this anymore, so I'm going to, I was going to comment it out. I think I'm going to delete this. We're just simply not going to be able to graph anymore, so what's the point? So we do XY, that builds the data set. We specify what our classifier is. Here, we're training our classifier. Now, I'm going to go ahead and add some stuff here. So in general, to kind of test how things are going, you do a training and then you do a testing. And testing isn't forward testing in the sense where we actually put this in real time and we see how it does. Actually, testing is done where we know what the answer is. We don't tell the computer what the answer is. We only tell the computer what the answer is after it's already made its prediction, and then we can see, were you right in your prediction or weren't you? So we're going to say, we're going to have a variable here called test size. And test size is going to be, you know, how much of this data do we want to have as testing data? So let's just say 500 testing data, and then we're going to say xy equals build data set. That's totally fine. Let's go ahead and print the len of capital X, so the length of X. The classifier stays the same, and then fit. Basically, we fit X minus, actually, sorry, X to the colon minus 500. Or no, I'm blanking out. Yeah, see, right. Okay, so the training size. Yeah, I'm confusing training and testing. Anyway, X, Y, and then again colon to the, and it's not minus 500. It's minus test size. Minus test size. And this will probably be the last video I filmed today. Brain's just too slow. CLF.fit. Right. So basically what we're doing is we're leaving the last 500 you know, data samples. We're leaving those. We're not going to test on those because that would be really silly, right? If you test the same data that you trained on, well, that's a bit of a mistake, don't you think? And some people think, well, as long as it's not exactly the same, like what if 80% of your data is non-testing data, but then 20% is the testing data? Like, won't it kind of average out? No, it will not. Don't do it. It will always skew your results. So anyways, CLF.fit. Then we're going to go ahead and do correct underscore count. Correct count is going to equal 0. And each time we do anything right, we're going to say congratulations, and we'll add the correct count. So then we're going to say for X in range. And that's going to be in range of anything from 1 to the test underscore size plus 1. For anything in that range, we're going to do if CLF.predict capital X minus X and then 0. So that's just basically what CLF predict. It always gives you the answer in a list, and we want the 0th element. That's the actual prediction. So if the prediction is identical to the value that we know is true, which is y to the negative x, we're going to say correct count plus equals 1. Then at the very end, we can do something like this: print accuracy, accuracy colon, comma, And then we do correct count divided by test size times 100.00. Now, let's make sure that's a full, yep. And that should be it. So, I cannot remember if we said we're doing the whole, yeah, we are going to do the whole thing. So, let's go ahead and save and run that, see what we get. Okay, so our entire list is 2,991 samples long, and we see our actual accuracy and prediction is just over 50%. It's 53.4. So let's make our sample size a little larger. Let's say we do, let's do 1,500. We run that, and suddenly we have a slightly more accurate reading there. Let's do 1,000. Let's see if how we do there. Right. So at about 1,000-ish, we see that we're doing okay. Now, this could be actually the result of a lot of things. One thing that you might consider doing it, well, no, that wouldn't change anything. Actually, okay, so now that I'm thinking about it, we do want to do one thing, and that would be after we've organized all our data in the data frame, what we're going to want to do is we want to randomize that data frame. So for example, when we look here, our data frame starts at A and it goes all the way down to Zynga. And the problem is, say we do, say we use half of the stocks for training, half of the stocks for testing. What happens? Well, at about this point, every stock up to JWN is trained on, and then every stock after that is tested on. That's not good. That's not the best way to go about this. So before we go training and testing, probably what we need to do is shuffle these up a little bit. Okay, so that doesn't work that way. So because it could be the case that these stocks, the lower numbered stocks are just different for any reason. Who knows? But basically what we're doing is we're training with a handful of stocks, and then we're testing on a handful of stocks that are not the same stocks that we just trained on. So that's just inherently a huge problem. So we can't do that. Curiously though, I do wonder, like, what if you trained, test size we'll say is, let's do the like 100. Okay. No, we can't really do that. So if we did this, right, if we just said testing is XY and we ran that, and then yeah, you get your answer. So we've tested, or we've trained on all of the data that's available to us, and then we just tested against the data that we've trained against. So some of the test we actually trained against, and we see our accuracy is 66.7%. So even with the randomization, dog is over here about to snore or something. I don't know. Sounds like he's in a fight or something in his sleep. Anyway, even if at our best case scenario, if we randomize this data, we might get up to 66.7% accuracy. But that's actually not that bad, all things considered. Even 60% accuracy, I'm pretty excited about that. That's not bad, considering. Even though the topic of machine learning, people say it's very complex. It's really not that complex, especially what we've done so far. I mean, within a few hours here of watching my videos, all of you are up to this point, and hopefully see that was pretty simple. So I'm pretty surprised that our accuracy is 63% at this point. But I do think it would be best to randomize up at least our testing sample. But then that causes problems, because actually what we want to see is into the future, not into the past. So that causes some trouble. Now, a few other things. We have a generic lack of data. We don't really have that many stocks. 500 stocks is nice, but that's not the best. Then also just looking in our stock files. I mean, some of these companies, we have like one update a year, something like that. A lot can happen in a year, so I wouldn't mind some more data. Also, I did do some looking around. Sadly, no one kind of pointed me in the right direction on the videos, but maybe someone still will in the future. But there are a few APIs that connects to Edgar, and there's a few examples of how to do it. that would be really, really cool to connect straight to Edgar, which is the SEC.gov's database of just data. So I'm really excited about that. There's also a lot of data we can get from Quandl as far as in terms of supersets and stuff, so we can do some cool stuff there. So we definitely have a lot of interesting things to think about and do in the future. We also have this slight probable issue with basically testing against stocks that we're not trained against. So we need to figure out that. And then probably do some other stuff. There's a few things that we actually want to do. We also might consider doing some more pre-processing as well. But most of what I want to do is get some better data and some more data, as well as fix the issue that we have down here. Also, we have a few issues as far as underperform and outperform is concerned. Should we use the last value, or should we use value each step of the way? If we are of the mindset that we should use underperform or outperform at each step of the way, we actually need to shift that entire column per stock. Because at the point of outperform, that means we should have invested in the stock at the previous set of values. Okay, so from 6 months ago, that's when we need to have invested. Because if we invest at the point of outperformance, that doesn't necessarily mean that you're going to get anywhere at all. So anyway, that's going to be it for this video. I hope you guys enjoyed. I'm pretty excited that with this kind of crappy code, apparently we have some darn good above 50% is exciting when you when you haven't written very good code here. 66 or 63% accuracy is pretty darn good. Now, before we get into making our code any more advanced than it already is, there's one more problem. So 66. Let me fix our issue here. There we go. That's a fallacy. We can't actually do that. I just was curious what the answer was. So let's say on 1,000 data sets, our accuracy is about 60%. Not bad. 60% could mean a lot of stuff though. What if, for example, we might pick 60% of the time we might pick winners that outperform the market, but what about the other 40% of the time? Are we picking people that still kind of perform pretty well with the market? So for example, 60% of the time we pick outperformers, I'm sorry, 60% is not picking outperformers. 60% is deciding whether it's an outperformer or an underperformer. So let's say our accuracy is 60% at picking outperformers in the areas, identifying whether they're an outperformer or an underperformer. What if, let's say, we find a handful of stocks that we believe are outperformers? We're going to be about 60% accurate on that. But then, how strong of an outperformer are those companies, right? And how bad of an underperformer are the ones that we picked and got wrong, right? So if this strategy is good at just recognizing in general good company structures fundamentally, then in theory, even the underperformers should underperform, but still perform pretty close to market, and the outperformers, in theory, probably perform close to market, but they might perform way better. But that's the question: is this is just a number of our accuracy? What matters more than your accuracy is what is the actual performance when you actually buy or sell. So a really good point made by gosh, I can't think of the guy's name right now. He wrote Anti-Fragile and stuff. But anyway, his point is, you could be your accuracy could actually be 10%. But if the things that you're right on, give you times 10 back, then congratulations. And conversely, you could be right 90% of the time. But what if that other 10% of the time you lose, 50 times all the money you just made? That's no good. That's just worthless. So in the case of investing or trading or whatever, your accuracy is actually pretty insignificant. What really matters is your performance and how well did you actually do in practice. So we need to build with this kind of investing in mind. We actually have to build a backtester and test it against actual data and see not only how accurate were we in our predictions, but what was the actual outcome as far as making investments on those predictions, because those numbers could be totally different. We could find that this strategy is 60% accurate, but it loses everything in a month, or we could find that even though it's 60% accurate, the losers, so to speak, are barely losers and the winners are massive winners. We just don't know at this point. So anyways, those are some things to think about moving into the future. Anyway, if you guys have any questions or comments on this video, please feel free to leave them below. Otherwise, as always, thanks for watching. Thanks for all the support and the subscriptions and the donations. And until next time.